Hello and good evening, and welcome to the final presentation from the ESS Group regarding Bartlett Pond here in Plymouth, Massachusetts. We're going to just do quick introductions for the folks that are up here in the front. I'm Karen Keene, Director of Public Health.
David Gould, Director of Marine and Environmental Affairs.
I'm Rich Brazel on the Bartlett Pond Committee.
Christine Bostic, part of the Bartlett Pond Working Group. It is on.
Ed Aluso, I'm on the working group.
Alice Bagman, the working group and chairman of the Minimet Village Steering Committee.
Thank you very much. After the presentation, I'm sure there'll be some questions. I just remind all folks to make sure that you press the green button before you speak, because the meeting tonight is being recorded for PACTV. It is not going to be live. It will be recorded and played at a later date. Those dates I do not know of at the moment. We have a question from the audience.
No request.
Okay.
You ask everyone to make sure that they speak and pull their mics right up to their mouth. Otherwise, we won't hear them and they won't hear them.
Okay, great idea. If you could please bring the microphone close to your mouth so that's recorded for PACTV, and also the folks in the audience can hear you. And when folks want to ask a question, we would also ask as well that you proceed to the podium and introduce yourself, and then make sure your green light is on as well. All right, thanks. And without further ado, I will now turn the presentation over to Matt Ludwig from ESS Group. Thanks, Matt.
Because I don't mind sitting up there if it's better for everybody.
Okay, go ahead. Perfect.
You have the remote, right?
Perfect.
Try not to hit anybody in the eye with the laser pointer. Okay, can everybody hear me okay? It is on, yes. All right, well, thank you for coming out tonight. I've been here a couple of times, and I got to say it's a relief to actually have some data to share with you and have a more complete story on Bartlett Pond. It was very exciting to get started with this project about this time last year, give or take a month, and to present some of our interim results last summer. And we feel we have a more complete story of what's going on with the pond, and happy to share that with you tonight. So thank you for coming. All right, so for folks who may not have been here or who just forgot at previous presentations, quick recap of what we're doing here. At Bartlett Pond, the sources of water quality and public health issues needed to be better studied to bridge data gaps. There have been rumors of water quality issues in the pond for decades, and there have been a few measurements, but nothing really comprehensive. So that's sort of what this study set out to do, set up a comprehensive baseline data set. This project considered near watershed sources, so things that are close to the pond, far watershed sources, the things that are more distant, seasonal anoxia and sediment release of nutrients. So that's just the seasonal lack of oxygen potentially in certain parts of the pond, and any release of nutrients that might occur because of that. And then possible intrusion of higher salinity waters into the pond, which had been suspected, and I think there had been lots of anecdotal evidence of, but we didn't really have any measurements confirming that. So the results of these things will be presented today. And this project will recommend management actions to address the key issues and support restoration of the recreational, ecological, and economic viability of the area. Our initial recommended actions will be presented tonight. For those of you who are familiar with the timeline, I cut this in half and just show mainly the 2020 portion of it, because our field program was entirely in 2019, as you'll see in the next slide. But as of November, we sort of considered our field study to be complete, even though we did end up going out a little bit after that. And we've been working on the report over the winter and some of the modeling that we'll present tonight. And so we're down here now, today's presentation, the draft plan being presented to the public. And after that, if there's any changes we need to incorporate, we'll revise that management plan, and then we have implementation schedule and essentially the final implementation schedule due by the end of June. So there may still be a few things left to do here. So some of the key project questions that we wanted to answer. What are the baseline water quality and biological conditions of Bartlett Pond? What is the relative influence of groundwater versus surface water versus internal loading of nutrients? So we knew all of these were potential sources, but how important were they relative to each other? What should we be focusing on? How often should algae blooms be expected to occur? So we know that one occurred in 2018, but we don't know how frequently they should be expected to occur. And would that be the same if we changed the watershed a little bit, or would it be different? And then are per and polyfluoroalkyl substances, better known as PFAS, and phthalates present. So these are sort of emerging contaminants. And then finally, what can be done to improve the pond? So as many of you know, this is a comprehensive study. We ended up sampling a lot of things, maybe some that we may not need to look at again, other things that turned out to be really interesting. I'm calling this sort of the A to Z, even though technically it's A to S. But we've got algae, aquatic plants, bacteria, bathymetry, benthic invertebrates, cyanotoxins, emerging contaminants, that's what I mentioned before, the PFAS, and a lot of water quality, just general water quality in groundwater, pore water, stormwater, surface water quality and quantity. So we looked at how much water is coming in addition to what the quality of that water was. And then sediment cores. And the sediment cores we collected specifically for what's called phosphorus fractionation, which we'll present the results of later on. But basically looking at the different kinds of phosphorus in the sediments. And then where did we sample? So we didn't go up the entire watershed, but as this first study, we sort of decided to focus here from the Tidmarsh site, which is located in the far bottom left corner of this aerial photo, down Beaver Dam Brook to State Road, and then what we were calling the inlet site, which is actually at Brook Road or Brook Street, and then Taylor Avenue, the crossing down there, we called the outlet. We had a number of stormwater sites, which we'll get into a little bit later, along the pond's edge. And then we had a bunch of different sampling sites within the pond itself, which are shown here in more detail. Sediment cores, water quality locations here in sort of the aqua color, groundwater segments in the reddish triangles here, and then benthic samples, these B5, B4, B2. So we've got really good coverage of the pond. This isn't even showing all the places where we took bathymetric measurements, which is water depth, and mapped plants. So we got pretty good coverage of this pond overall. So that shows the spatial coverage of where we sampled. When did we sample? And this is looking at last year, starting in April over here on the left and going into December. This is laid out by the tasks that were in the original contract, but I can go into more detail if people want me to. But essentially, you'll see we were out there pretty much every 2 weeks from April to November doing something. Sometimes we were doing mapping in the pond. Sometimes we were doing water quality sampling in the pond. Sometimes we were doing upstream and downstream sampling in Beaver Dam Brook. We did 2 groundwater assessments in the spring and the fall. We did fluorosurfactant and phthalate sampling in the spring and the fall. We did our sediment regeneration monitoring, which is really the phosphorus fractionation, which I introduced before, the cores. That happened in the springtime. And then we had 2 stormwater monitoring events, one in July and one in December. And the one in July was a big storm that followed an even bigger storm. So that was a pretty good slug of stormwater that came through. The December one was a little more humdrum, but a different season. So it kind of gives you a sense of some of the seasonal variation there. And then for most of the summer, this was an optional task that we ended up completing for the town. We did what's called cyanotoxin testing. So this is not looking directly at the algae, but looking at the toxins that the algae might produce under certain conditions. So we actually did 6 rounds of that. So if nobody has any questions on that, we can go ahead and start talking about the results. So I think we did share this slide previously, but I just want to go over it real quick because there are some important takeaways here. This is bathymetry, just water depth of the pond. The main takeaway here is we've lost 1 to 2 feet of water depth since 1970. So we now have a maximum depth of about 4.1 feet, give or take, you know, what the water level actually is, and an average depth of 2.4 feet. Well, back in the 70s, it was 6 feet deep in the deepest location and average depth of 3 to 4 feet. So we've lost a decent amount of the pond volume. Right now, we're still standing at 3.2 million cubic feet, which sounds like a lot, but it's a lot less than there used to be. And it means that we have a detention time, which is how long the water is actually staying in the pond, of just a few days. So water comes in and flushes very quickly out of the pond. And you'll see that'll be kind of a central focus of tonight's presentation. That affects the pond in lots of ways, some good and maybe some not so good. Yep. I'm fine, it's up to you.
I was just curious what attributed to the volume loss.
We're not exactly certain on that, but there could be a lot of different things that contribute to it. Definitely, if you have a nutrient-rich system, which you'll see this is, you have a lot of production of organic matter, which can fill a pond over time. Also, if you have a lot of erosion from the watershed, that can bring in sediments. If you have backflow from the ocean, you can also get some of that introduced periodically that way too. In fact,
What about dredging out the sand that blew in from the nor'easters?
what about dredging it out?
Okay, people aren't gonna hear you on the recording unless you go up to the podium.
You want me to go to the podium
Please.
and ask my question?
Yes, please. Thank you.
My name is Robert Crone. I live on the north side of the pond. I know that they had dredged it out last year or the year before, the sand that migrates up there from the nor'easters, and it's right at the mouth on the west side of the Taylor Avenue. And I noticed, you know, across the way there where the sand has built up. Okay, so I thought I had it on. It was on. Okay, and it used to be, if I walked over to the pond, it was probably this deep with the sand being underneath. And then when the town came in and they dredged that all out, they took all the sand out of there, then the water started flowing out there. I think that's at that time I probably noticed maybe after it had completely cleared that out, all the sand that was there, then they banked it on either side of the channel there, the inlet that comes right out of the pond. I was just guessing that there was an 8 to 10 inch drop in the whole volume, the level of the water back then. That's when they did it last year or the year before. I think it was 2018, I think they did that. So I figured if we lost this much, this is probably just from that one shot there, and I don't know if there's anything else that had contributed to the total volume loss besides that.
Definitely, I think the right kind of nor'easter could push sediment into the pond, yeah.
Yeah, right.
In addition to
No,
all those other factors that are
yeah.
contributing.
And like I said, I mean, I've been there since 1972, and I did notice that, you know, the buildup was there, and I think this is the first time that the sediment, the buildup was ever taken out of the pond, and I did notice that drastic change in the volume itself, so that to me was a contributing factor.
And I think there was actually a study that we looked at where there were cores collected from Bartlett Pond a few years ago. And they tried to age the cores, and you could see the blizzard of '78 had a signature in those cores that were collected. So one of the things that we measured was stream discharge. And we did this a couple different ways. We set out water level loggers in the inlet and outlet locations, so coming in into and flowing out of Bartlett Pond. And then every time we went out to do in-stream flow or water quality measurements, we also measured the flow. So over time, we were able to develop a relationship between the discharge coming out the stream and the level of the water. And so we were collecting those water level readings with the loggers very frequently, so we had multiple measurements every day. And at the end of your record, when you correct them for the actual discharge coming out, you get a graph like this. So you can actually see what the flows were like coming through the inlet of Bartlett Pond in the springtime. Here's that big 5-inch plus storm that we had in July, early July, and you see the big spike in flow there. I also want to show you this thicker light blue line. This is what we're calling the base flow line. So this is essentially groundwater coming into the stream system and keeping that stable base flow going. And you'll notice that it doesn't really drop very far below 10 CFS, cubic feet per second, the entire year. So we have a system, at least this year, with plentiful groundwater coming in, as well as a lot of storm flows on top of it, that sustained a very continuous, fairly decent flow for most of the year. One thing you will notice is the size of these spikes, except for this 5-inch storm, are pretty small compared to this base flow. So you're not really, sometimes you're occasionally doubling the flow, but not really higher than that. So that indicates that Bartlett Pond has a signature response to storms, but it's not really super flashy, which is important to know in terms of how nutrients and sediments come into the pond and what we can expect future flows to be like as well. This graph down here is just the outlet. So you'll see it's pretty comparable to what's going on in the inlet. There's a few things that don't quite match up, and I don't know exactly what all those are. Some of them are storm events, and some of them may be other things. But they do match up pretty well, which sort of helped us figure out that we had pretty good data there. But in general, you've got more water flowing out of the pond than you have flowing into it, which means something's happening in the middle too. And what that is you're getting both direct rain on the pond, but you're also getting groundwater flow directly into the pond from the areas surrounding it. Just before we move on, I want to note that this was really kind of an unusual year in that we had very consistent rain most of the year. We had large storms. We had a number of 1-inch plus storms. I think there were more than 60 events where we had more than 1/10 of an inch fall. So there weren't really any true dry periods this year. There were times when it was drier than not, but I think the maximum number of days in a row with no rain was maybe 2 weeks during the middle of summer, and that's not really too bad. So things didn't get too droughty this year. All right, so now looking at water quality in the pond. We also deployed data loggers in the middle of the pond. They measured things besides water level. One of the things was temperature, so that's this orange part of the graph. This grayish line is conductivity, which is kind of a surrogate for salinity. So whenever you see those gray lines spike up, that's salt water coming into the pond. Now, it's not as salty as the ocean, but it gets pretty salty here towards the end of the year in November. And you got to remember one thing: this logger was in the deepest part of the pond. So if there is salt water in the pond, salt water is denser than fresh water. Salt water will sink. So this is not to imply that the entire pond turned salty or brackish during these times. Just that the deepest part of the pond had some salt influence. So we definitely saw that coming in, but only really from late or early August on. We also had periods of low dissolved oxygen. So this is what we were referring to before as anoxia, both in the summertime, which is mainly a diurnally driven thing, where at nighttime you would have a lot of organisms in the water respiring, so they're all breathing like us, but you don't have photosynthesis going on, so you'll lose dissolved oxygen from the system as it gets consumed by those organisms. And then swinging back up during the day as the algae and the plants start to photosynthesize again and put oxygen back in the water. So we had a few times here where we dropped into definitely the low DO category, which is less than 5 milligrams per liter of dissolved oxygen. But we also had some nights where we dropped basically into the anoxic part, which is very low dissolved oxygen. Almost really not enough oxygen to move forward the processes that organisms like us like to do. So that was not unexpected. what was a little unexpected was seeing these drops in DO towards the end of the year. And you'll see that those kind of coincide with this major slug of salt water that came in. So what exactly was happening there, we're not totally sure, but it may be that there was a separation of layers where the denser salt water sat in the bottom, and the biological processes that go on in the bottom sediments just continued going on, and there wasn't mixing of the water, so there wasn't any new oxygen coming in for that period of time. That's one theory. Over time, we eventually started losing that salt again. As you see, we do that, then we get more mixing of dissolved oxygen back down into those deeper waters. So all this is to say, we have at least brief periods where we seem to lose dissolved oxygen in the bottom of the pond, in the deepest part of the pond. It may not happen everywhere else. But this is important in terms of how the chemistry in the pond works and how the biology of the pond responds. We also looked at more traditional measures like bacteria. So we measured enterococci, E. coli, and fecal coliform, which are all typical beach bacteria monitoring indicators. There's not actually any public swimming beach at Bartlett Pond, but as we all know, the pond discharges onto White Horse Beach. So these are still relevant in terms of what's happening in the pond before it gets discharged out into the beach. Enterococci are usually used for saltwater beaches. They tend to be tolerant of salt water, whereas some of these other indicators are not. So that's the top graph here, and you'll see in that graph, we had some spikes early in the spring, but nothing that really exceeded this threshold here, the orange line or the gray line. Then in the summertime, following that big storm in July, we got a big spike, and then it crashed down again. And then we go up and down the rest of the season. So we get these slugs of enterococci that we're finding in the pond. But I think looking at the results that the town collected in the Bartlett Pond outlet, we didn't really see that much enterococci coming out of the pond. So something was happening where the bacteria apparently were not discharging out into the beach, at least based on the measurements that we have. E. coli and fecal coliform basically had the same pattern to each other, but they were different than enterococci in that during the summertime, we essentially didn't have any exceedances of E. coli or fecal coliform. Those were mainly confined to spring and fall. So enterococci definitely had our highest counts in the summertime after that big rainfall. Now looking at nutrients in the pond and a little bit about what's coming in and going out, because it's kind of nice to be able to compare those things. The overall story is we have lots of phosphorus and we have lots of nitrogen. The phosphorus levels are particularly elevated. Most of our measurements showed that there was more than 0.04 milligrams per liter, or more than 40 parts per billion, which doesn't sound like a lot, but it really is a lot because it doesn't take much phosphorus to make a lot of things happen. And in fact, if you look here on this graph, we actually inserted what's called the Cape Ponds limit. It basically comes from a study of the Cape Cod ponds that was done earlier in around 2001, I think. And if you're above that line, it means that your phosphorus is probably a little not on the good side. If you're below that line, you're in good shape. So you can see we're way, way above that line. I mean, we knew that already, but I just wanted to kind of put it up there as a comparison so that everybody could see how far above that line that we are. On the nitrogen side, we're flirting a little bit with the Cape Ponds limit, but we're still pretty high. So we've got lots of phosphorus and lots of nitrogen. The phosphorus tends to increase from the inlet to the outlet. So it comes in Beaver Dam Brook at a high level already, goes through the pond where it picks up more, and then discharges out the outlet, and there's even more phosphorus. That peaked in July, which we see here. And again, this potentially could be related to that same storm system that we talked about. Nitrogen, most of our measurements were more than 0.03 milligrams per, I'm sorry, that should actually be 0.3 milligrams per liter. So drop the zero, the zero right after the decimal point there. But the spatial trend there is less clear. So we have different species of nitrogen. We've got nitrate, we've got nitrite, we've got ammonia, we've got total Yelldal nitrogen, which is ammonia plus other organic nitrogen. Those things can all vary independently, and that gives you your total nitrogen number, but what you might actually be seeing here is peaks of different things at different times. And in fact, this peak in the summertime in nitrogen was really coming in, was really mostly TKN, so that's probably a lot of particulate matter coming in from that storm that got flushed in. Whereas during the spring and the fall, it was more nitrate related. So we know we've got lots of nutrients, but what does that mean, nitrogen and phosphorus? And what does it mean specifically for algal growth, which is the thing that we're kind of all questioning here? Well, there's lots of potential to grow algae, but if we look at what's called the Redfield Ratio for more clues, we can sort of figure out what's really kind of controlling the algae growth. The Redfield Ratio just basically says, what's the typical ratio of these nutrients that's actually found in algal cells, assuming that they're going to take up the nutrients in the ratios that they need to actually maintain their tissues. So that sort of varies. The traditional Redfield ratio is 16. That's what most people use. I lowered it a little bit here just because that was based on marine waters, and we're not really into marine water. But essentially, somewhere in this area is where you would expect to see the Redfield ratio. If you have a higher ratio of nitrogen to phosphorus, then you've got what's called phosphorus limitation. It means your phosphorus is relatively in short supply compared to your nitrogen. And if you're below it, you've got nitrogen limitation more likely, which means your phosphorus is in relatively high supply compared to your nitrogen. So as you can see over the course of the year, and we'll have more detailed results than this, these are just based on our point measurements that we took over the course of the year, and the modeling will sort of help elucidate how this might have varied over time. But in the springtime, you're relatively phosphorus rich, nitrogen rich, and in the summertime, we're relatively phosphorus rich. So what that means is if you're phosphorus rich and you add a little nitrogen, you can make algae. If you're nitrogen rich and you add a little phosphorus, you can make more algae. When you have phosphorus that's so high above the nitrogen, like what we were seeing in a lot of our summertime samples, you have a lot of potential to make a lot of algae. All you need is a little extra nitrogen, and the algae can use that. And so you're basically setting yourself up for potentially an explosive growth of algae. We didn't see that this year, so why did that not happen? And that's kind of what we're going to get to soon. So when I say we didn't have an explosive growth of algae, I'm really talking more about cyanobacteria. We definitely had lots of actual other kinds of algae in the pond. And these are the chlorophyll A measurements that were taken from a logger in the pond over the course of the year. And you'll see we started out actually really high in the springtime. We had a diatom out there that's called Stephanodiscus hanskii. That bloom lasted from May to early June and probably made the waters pretty turbid. You might have noticed that the pond looked a little brown. That lasted for quite a long time. And then our chlorophyll A levels dropped off for most of the rest of the summer. We had little spikes here and there, but not really until late fall do we start seeing sort of more consistent signals than that. So essentially, we didn't really have much of a summertime algae bloom. We had springtime and fall. And springtime algae blooms typically aren't harmful algae blooms. I don't want to say that they never are, but they tend to favor species more like diatoms, which is what we saw. Summertime, that's when you would expect to see more of your cyanobacteria, the blue-greens. We didn't really see them this year. Possibly into the fall, but we didn't see them this year in the fall either. So the takeaways, no cyano blooms were detected in 2019, but we had plenty of algal growth. We only had actually one of our 9 sample rounds where we collected phytoplankton. Did we actually find any cyanobacteria, which is a little odd, because usually they're around, they're natural, they're going to be in most water bodies. We just didn't find very much this year. We did find some growing in the, you guys have probably seen the algal mats growing on the bottom of the pond. There were some filaments of cyanobacteria mixed into that, but they weren't taxa that tend to be toxigenic, so that was good. And they weren't present for very long, actually, from what we could tell. And again, that was just a qualitative analysis. And then all of our cyanotoxin tests, which would come back positive if there was something that we just couldn't see that was producing toxins in the pond, they all came back negative. So they were all well below the detection limit. which is again well below the recreational standard set in Massachusetts. So this year we looked pretty good in terms of harmful algal blooms, but there's definitely a lot of algae. So you'll see we're well above the Cape Ponds limit here pretty frequently. Now these figures here, I don't want people to get too caught up in the details because these are concentrations, they're not loads. So that means concentration is how much is in the water right now if I grab a drop of water. The load is really the most important part, but we think of water being dirty in terms of concentration, so that's why it's expressed that way here. The load is how much of that pollutant that you're looking at is coming into the pond over the course of a month, a day, a year, whatever it is. So that's really the more important thing because that determines how the lake is going to respond, or the pond. So what we see here is we have this is phosphorus. Tidmarsh, we're already quite high in phosphorus. We only collected 2 samples there during stormwater, so of course these are probably likely to be the dirtiest samples that we get because stormwater tends to have more phosphorus in it than dry weather flow. But still, we had plenty of phosphorus. We were at 110 parts per billion, or 0.110 milligrams per liter at Tidmarsh. And then as we travel down through the system, we get a little bit of thinning in the phosphorus at State Road, but it's really not it's not like it's clean or anything. So we're down to 93 parts per billion there. And possibly a little more dilution at the inlet, 73 parts per billion. But again, here at the inlet we have 11 samples. So this is combining all the wet weather and dry weather samples. So this inlet number is really kind of pulled down by those dry weather samples that tend to be a little cleaner. These big orange dots here, these are the stormwater outfalls. So Vinebrook Road, we sampled 2 different stormwater outfalls there. The one that's right near where we put our boat in is had the highest concentration of phosphorus that we detected anywhere in the study. And that was at 230 milligrams per liter as far as surface water goes. But all the outfalls had some phosphorus issues. And going through the pond into the outlet, you'll see we actually pick up phosphorus again. So at pond 1, which is our deep water location, we've got 73 parts per billion. And by the time we get to the outlet, we're at 88 parts per billion. And we have a lot of samples from there. We have 9 there. So there's phosphorus throughout the whole system, I guess, is the point I'm trying to make with this. You know, there's not really a smoking gun as to where is it coming from. It's kind of coming from all over the place. Even the rainfall, and I know we mentioned this the last meeting, we only collected 1 sample, so if we collected more, maybe that number would come down, but we still had 31 parts per billion in rainfall alone. Which is high, but it's not unheard of. Now, looking at nitrogen, we have a pretty similar story, actually, where we start out fairly high here at Tidmarsh, 0.665 milligrams per liter, again, based on 2 stormwater samples. We move down through the system. We actually pick up a little now at State Road, 0.935. And then by the time we get to the inlet, we've got, again, those dry weather samples are pooled in here. So it pulls our number back down to about 0.5 milligram per liter. And again, the stormwater outfalls have the highest concentrations. But remember one thing about stormwater, even though it might be dirty and it might have high concentrations, it's not flowing all the time like the stream is. So if it rains, and it rains a lot, you might get a dirty sample out of those. But then it stops raining and they stop contributing pollutants once they dry out. And we maintain nitrogen through the system, so it's still at about 0.5 milligram per liter when we get to the outlet. So again, similar story here, plenty of nitrogen throughout the whole system. Now looking at the sediment phosphorus regeneration, which really we did as sediment cores that were pulled out and then sliced up and sent out to Keith's lab for analysis of the different fractions of phosphorus. We collected 8 samples of those, or 8 sediment cores in early May. Excuse me. Each core was sectioned to provide vertical profile, and we got quite a number of sections in some of those bigger cores, so we were able to take a good look at the vertical profiles. And then we analyzed them for different phosphorus fractions. The main one that we were focusing on, we suspected would be an issue, is what's called mobile phosphorus. So this is the most easily released into the water column, especially during anoxic conditions. Excuse me. But we also did look at organic phosphorus and phosphorus bound to other metals like aluminum. And what we found is there is some potential for phosphorus release from the sediments through mobile phosphorus under low dissolved oxygen conditions. The highest surficial mobile phosphorus was found in central and southwestern sediments, so these areas down here, basically closer to the inlet. And then organic phosphorus was actually a higher fraction than mobile phosphorus. And this phosphorus can be released as decay occurs of those organic sediments. And just looking at this, we weren't sure what that meant, but the modeling will sort of help clear that up, and Keith will, I don't want to steal his thunder, but it turns out that the organic phosphorus is also important. And we found the highest surficial organic phosphorus in the northern and eastern sediments, so more in these areas. And with this, I'll pass it off to Jeff. I think my throat's not appreciating this, so.
Hello, I'm assuming everybody can hear me okay. Jeff Hirschberger, I'm a senior hydrogeologist with ESS, so I deal with the water that we don't usually see unless we pump it out of the ground. So again, I mean, as Matt has said, you know, we've got concentrations and loads. One of the aspects of the water budget we had to look at was what kind of contribution are we getting from groundwater into the system? Not only from a nutrient perspective, but there were some targeted emerging contaminants and organic contaminants that we wanted to look at as well. So within the pond, we did a couple different things to look at quantity and quality. I think we had explained these before. We use seepage meters, which are really, you know, the top third of a drum that you put in the ground, which gives you a fixed area, and then you put a bag on that, you fill it with water, and you look to see whether you lose water or you gain water from that system over a period of time. And that gives you your groundwater flow in that area. So we had 4 different segments that we did that in. At that same time, you see Stephanie up there, that's called a lip sampler. Littoral interstitial pore water sampler. So really put that down in, drive that into the subsurface, make sure we get that through the initial top sediment, and then we purge a little bit out of that. We take a look at some of the field parameters, conductivity, pH, to make sure it looks like it's different than the surface water we're also sampling at the same time. And we collect samples of that. So from the seepage meter, we get a flow. From the lip samplers, we get a concentration, and that can kind of give us feed into our load coming into the pond from groundwater. And again, as Matt said, a lot of the work we did was really focused on kind of near field around the pond. The groundwater work in particular was really focused on what's really coming into the pond in close proximity to the pond. We did these really along the shoreline of the pond. We did, again, 4 shoreline segments, so we usually will break up the pond in some reasonable shore segments. We had a couple kind of on that southern side of the pond that we considered kind of the inflow, typical inflow areas. And we had a couple on the kind of northern side of the pond that would typically be your more outflow. Again, with the ocean there, you get a little bit of tidal influence, a little back and forth in there, so you might get a little inflow, outflow over there as well. We did sampling in May and September. We wanted to try to get a feel for what the conditions were like under a couple different scenarios, typically a wetter period and a dry period. May not be that case when we did it this year, but, and we sampled those for the various nutrients, really looking at the nitrogen series and then phosphorus from the nutrient perspective. I'll get into the data a little bit more. We do have some areas of elevated phosphorus and do have some areas of elevated nitrogen in the groundwater. Those didn't necessarily match up with one another. May suggest some different sources, some different issues maybe where those are coming from. We had a general increase in phosphorus in our samples when you went from south to north. And we had a general increase in nitrogen in those samples as you went from east to west. So, not necessarily the same. And again, I'll get into it in a second here, but the phosphorus and nitrogen loads don't necessarily match up either, because you have to take into account the flow at each one of those locations, plus the concentration to try to determine what that load is. So again, in red here, you do see, oh, there it is. You see the 4 spots. We considered these kind of our up gradient side of the pond, with groundwater flow typically being from the southwest to the northeast. You would expect most of your inflow to be on that side, this side of the pond. And in a typical pond situation, your outflow would be focused on the down gradient side of the pond. Here again, we have the ocean in close proximity. We've got to deal with the tidal fluctuations in the groundwater, so it could impact the inflow-outflow conditions, particularly on that northern side of the pond. Groundwater GW1 here was kind of considered a background location. It's a little less developed area around the pond. What we ended up finding was, as we expected, highest groundwater fluxes in here, both spring and fall. We had some groundwater flux entering the pond at these 2 locations, lower, but some coming in the spring, in the May event. In the September event, there was almost no flow at both of those locations. As far as nitrogen, as I mentioned earlier, our nitrogen generally increased from the east side to the west side. So we had our higher nitrogen up here at GW3 and GW4. GW3, as I mentioned, limited flux, so the load coming in from that area is lower. But we did have some pretty good flux coming in from GW4, which could suggest that there could be some good nitrogen contribution in that area into the pond from groundwater. Again, phosphorus was a little bit different. Phosphorus tended to be higher on the northern side of the pond. So again, higher at GW3, higher at GW2. Again, limited flux, limited flow in those locations. So groundwater doesn't necessarily seem to be as much of a contributor of phosphorus into the system as it might be for nitrogen. What else did we look at? We also were going to task to looking at the very popular PFAS contaminants and phthalates, another organic chemical that you find in fuel oils, and you find them in incomplete combustion, some other sources. And we were tasked with sampling those. So one of the things we looked at was, okay, what is our watershed that we're dealing with? What are potential sources of any of these types of compounds that might be in the watershed? Interesting thing, in a lot of the watersheds that we work in, the ground watershed and the surface watershed are very similar. That's very common in a lot of the smaller, kind of self-contained watersheds that you see in Massachusetts. Not so necessarily down here in southeast Mass or on the Cape. We have some of these extensive sand and gravel aquifers with kind of undulatory surfaces on top of them. So you get a lot of cases like we have here, where you get a surface watershed, which is in the light blue here. It takes on this shape, which is really where's our surface water flow that's eventually running through Bartlett Pond, versus our ground watershed, which actually ends up going off the figure here, which is oriented this way, which really is taking water from a high knob of groundwater in the middle of the town, and then that feeds to some of these sub-watersheds that feed off into some of these different ponds, or in some cases just merely discharge to the ocean. A lot of that delineation work was based on some extensive modeling that USGS has done in the area, looking at the Plymouth Carver Aquifer, obviously a very important source of groundwater. So they've done a couple different rounds of modeling here, and that was used by not only us, but also by the town to try to delineate some of these ground watersheds. So again, unlike some of the watersheds that we've worked in, not a lot of industry as far as being in this watershed, but there are some things that could contribute to some of the water quality issues here. We do have a couple larger groundwater discharge permit sites, which are really combined septic system type discharges for some of the larger facilities. Plymouth High School, Plymouth South High School right here, and also Village Crossing condominium complex up here. We do have the old Plymouth Manomet landfill, sits right at about this area here. We do have Pine Hills, obviously very prominent in the upper part of the groundwater shed here. All of their wastewater gets discharged to a wastewater treatment plant here, then injected into the ground in a series of wells, and then supposedly captured by a series of down gradient wells and then reused back on the golf course. In theory, that's how the system is supposed to work. Moving then down closer into the pond, we do have some, sites here with underground storage tanks. Not to say that any of those are leaking, but they're there, they're present. We have some of those, it's a couple of the gas stations here, Churchill Oil and Gas, and then up here at 7-Eleven. There is one Massachusetts contingency plan state waste site, but again, I reviewed most of the information there, not a significant widespread issue at that site. Looks like it was a fairly localized release. Manomet Car Wash, really why that was put in here, it can have some, not all, but some car washes supposedly, and some of their waxes that they had used did have some PFAS type components to them. But again, it was not everyone, different brands, it's really hard to pinpoint, what was used here.
What's that big pink area I'm seeing?
Oh, that pink area is part of the Tidmarsh restoration area. I think that's the appropriate delineation there, if I'm not mistaken. Is that all Mass? Okay. And then the fire department is on here just because fire departments often did fire training, things of that sort, where they used the foam that contained PFAS. I don't think a lot of fire training was done here, so I don't know that a lot of PFAS applications or any foam applications would have been done in this area. And again, with PFAS, we'll get into this a little bit more. Oftentimes it's hard to pinpoint sources because it's so prevalent in everything we've used and everything we consume. You can get a lot of this from septic systems. You can also get a lot of this applied at various automobile crashes, things of that sort, spot places that there's not good records within the watershed. But one of the things we wanted to do was really just try to look and see if we could get an inventory of, what's in the watershed. And a lot of them that we've studied, this isn't that bad. There's not a lot of sources in here, so. And again, as we just talked about, PFAS and phthalates were a couple of the things that we were tasked with. PFAS is obviously an emerging contaminant. What makes them very difficult is they're very mobile, and they don't really degrade. It's very much like PCBs when PCBs were an issue. When they were manufactured to be persistent, to last. Same thing with PFAS. Used in a lot of different applications, waterproofing, Teflon, stain resistance, firefighting foams, some waxes. I mean, I could go on and talk about that for a long time. And there's a lot of good information out there now. I must admit, I probably get at least 1 or 2 emails every week about some new things that are coming out with PFAS. So the nice thing is there's a lot of good people, a lot of very smart people working on that problem to try to help us figure it out. Phthalates are very different. Phthalates are used in many industrial and consumer products. It's a plastic. It helps to get into plastics. I had sampled on a Monsanto site that had a free-phase release of phthalates, and they're pretty nasty. They aren't as mobile as the PFAS are. And the nice thing is, with phthalates, it's a pretty easy story. We sampled stormwater, we sampled surface water, we didn't find them at all. And we sampled, the detection limits we had at the lab were very low, so I'm very confident that there really isn't any significant phthalates in the watershed, which is a good thing. We sampled surface water twice, and we sampled stormwater twice. We had originally scoped it out to sample some additional times. We cut back a little bit on what we found in the spring. I'll talk a little bit about the results, I think, on the next slide. Actually, I wanted to lead in a little bit with the standards, because again, we talk a lot about concentration, and there's a lot going on right now in Massachusetts as far as regulating PFAS. They're on the verge of coming out with a drinking water standard that's 20 part per trillion. So again, a lot of the stuff Matt was talking about was at the part per million level. This is going down to the not part per billion, which is the next thousands down, but down to the part per trillion level. So we're getting very small as far as the concentrations we're tracking now. But they're setting up a drinking water guideline, which is going to be 20 parts per trillion, which is going to be the total concentration for 6 of the PFAS compounds. Now again, that's 6 out of about over 4,000 compounds that are out there of PFAS. And the other thing that's making this a moving target is that none of the manufacturers wanted to give up the products that they were selling, so they're coming up with replacement chemicals for PFAS that we're now having to try to find in the environment. So that's very interesting. Massachusetts has also come out and set soil and groundwater standards under the Mass Contingency Plan for waste sites, disposal sites. They set the RCGW1 and Method 1 GW1 standards are to be protective of drinking water. So those are set at the same threshold as the drinking water standard will be. So 20 part per trillion for those 6 compounds. They've also set what they call RCGW2 and GW3 standards, which are to be protective of discharges to surface water. So again, looking at somebody being exposed to that water in a surface water environment as kind of a recreationist, a trespasser, and also looking at the ecology, how sensitive is the ecology to these contaminants. And the one thing you'll notice is compared to the 20 part per trillion for drinking water, which is really us ingesting that water over a period of time, it's a lot more sensitive there, 20 part per trillion level. When they set the levels for discharge to surface water, they're at 540,000 part per trillion. So as you can see, through that environment, it's not as sensitive in exposure. So those thresholds are a lot higher. And again, that helps us a little bit as far as what we're looking at for Bartlett Pond. So from a Bartlett Pond non-drinking water scenario, it can probably handle larger, higher concentrations in that environment than you could if you were drinking this material. EPA has come out with a advisory level of 70 ppt part per trillion. They only cover the 2 primaries, PFOA and PFOS, and they're getting a lot of pressure to come out with MCLs that are more in line with what other states are putting out there. And a lot of other states are coming out with lower thresholds. I've heard thresholds as low as far down as 7, and some are even looking at other things. But again, I take all that with a grain of salt because we're moving with setting these standards in a lot of cases before all the supporting health information is coming out. So they're kind of doing that concurrently. We do have a lot of information that says that these things can be nasty, so I think they're appropriate in setting these things low. But again, those will probably gravitate a little bit as we get more information on how these things behave. Now, what did we find? In surface water, we did find some detections. We didn't see anything in the spring sampling when there was higher water flow, higher pond levels. We did see some PFAS when we did the sampling in September. I think it was September. It was later in the year. We did sample for all 6 that are regulated by DEP. We only saw PFOA and PFOS out of those 6. All the detected concentrations were well below that 20 ppt threshold that we saw for drinking water. And if you think about the 540,000 for discharge to surface water, well below those. If you think about it, the concentrations that you see up there that we saw were in the 1.76 to around 2 part per trillion, just above the detection limits. Our detection limits at the lab were about 1 part per trillion. So again, we're looking at really low concentrations of these. And all the field QC was good. One of the things they're finding is with their prevalence in a lot of the consumer products, you have to be very careful how you collect the samples. There's certain gloves you can't wear, there's certain clothes you can't wear, you gotta be careful what you eat because of food packaging. So all the QC, the field blanks and everything came out well, so that's good. We also sampled in stormwater, so we did 2 stormwater events. One was in July and one was in December. Again, we had detections in both. We had more detections in July, but we did have detections in December as well. Again, most of our concentrations were in that around 2 part per trillion level. We had 1 detection of what's called PFBA, the top one on the table there, that was at 20. That's not a regulated compound at the moment. And again, from the surface water environment perspective, I think I'd look more at the 540,000 that DEP has set. We're well below those thresholds. And again, a lot of the concentrations we're getting and we're seeing out here, there's probably not a real source of this material. What we're finding is it's prevalent in the environment. You get this from atmospheric deposition. You get it from people's septic systems. You get it from just all the uses we have of this. There's just a lot of sources of this material in the environment. And it's not that uncommon to see it at these low part per trillion levels in a lot of places. So I think what we're seeing here, it doesn't alarm me. I'm not surprised that we're seeing it in the environment. But I don't think it poses any kind of a problem for Bartlett Pond at these concentrations. But again, I think it's good to know that we've done the sampling, and this is kind of what we found. At this point, is it back to Matt? Any questions on the groundwater while I'm up here? We'll certainly take questions after as well. Thank you.
All right, so now that we're through a lot of the water quality, we're going to get back to biology for a moment, and then we'll hit the modeling. Aquatic plants in Bartlett Pond, we didn't find a whole lot compared to what had been found back in the 1970s. This used to be, according to the report that was done at that time, a heavily plant-dominated pond with lots of yellow water lily. In fact, it almost sounds like it was growing at nuisance levels. When we went out, you'll see all these white points. These are points that had no aquatic plant growth whatsoever. The points that have yellow, orange, green, those are different densities of plant cover. There's not a lot of very dense beds in Bartlett Pond. Most of the beds that we found are very small, sparse. The good news is we did find actually a decent diversity after we scoured the pond a few times. So we came up with a nice plant list. The first time we went out, there were almost, there was 1 or 2 species. I think at the end of the day, we got up to 10 or so. So we did okay. And these points don't really include some of the more obvious plants that you might see if you're recreating on the pond or if you live on the pond, which are the things that poke out of the water, like water willow. There's a lot of that here. That's not shown in this map, but we know it's out there. And there's a number of other emergent invasives too, like common reed, also known as Phragmites, and purple loosestrife. That's that really beautiful purple flower that comes up in the late summer, and you can tell why people wanted to have it in their gardens, but it's escaped gardens and gotten all over the place. It's very easy to spot when it's in bloom. So that's aquatic plants. We actually pulled together a field guide to the aquatic plants of Bartlett Pond. That'll be part of this report. So if people are curious to see what they're looking at in the pond, you can use that field guide, hopefully to figure out what it is that you're seeing. It's the stuff that we saw in one season, so it doesn't mean that other things couldn't be there at some point, but it'll at least give you a place to start. It also includes a number of potential invasive plants that could be seen in the pond in the future that you'd want to keep an eye out for, so that we can do something about them before they become a problem. And speaking of invasive plants, we found 2 exotic invasives, not in the pond, but in Beaver Dam Brook. We weren't expecting to find them there. They're a little unusual to see in that spot because the water's flowing. You usually don't see a lot of floating aquatic plants accumulating there. But this plant on the left is water lettuce. That's an exotic species. And this plant on the right, which looks fairly similar, but it's a little glossier and darker green, that's water hyacinth. It's the same plant that down in Florida choked out a bunch of huge waterways. I don't think we would expect to see the same thing here because even though we didn't have a very cold winter, normally winters get cold enough that these plants don't really hang around and they can't do very well in nature here. But as we know, climate is changing and conditions may become better for these plants in the future. So it's something we want to keep an eye on and, if possible, get rid of when they do come into our systems, because plants like these could be very destructive to a natural water body in that they sit at the top of the water column, they shade out everything underneath them, and if you have a solid cover of them, you can quickly lose dissolved oxygen underneath those, in addition to all the other ecological impacts. Yes?
Question for you on the water hyacinth. Is there a possibility that maybe remnants of somebody's aquarium?
It's a very high likelihood.
Yeah, okay. I haven't seen any, at all, ever, in my area, so that's why I'm questioning.
I think one thing, we weren't able to track this up the stream this year, but it's something that may be worthwhile doing if we see it again next year or in the future, to try to find what the source of it is. It could easily be an ornamental pond that's spilled over or gets dumped on a regular basis or something like that that's contributing as the source. Once you have a seed bank, then you're kind of in trouble. So you want to avoid establishing a seed bank in the system. So sooner is better with these kinds of plants. Yep. As I mentioned, we did see some exotic emergent plants too, the purple loosestrife, the common reed. But we did have native plants in the pond. Most of them were small, like this nice little slender milfoil. That's about the smallest milfoil you ever have. Most of the other milfoils are big and get in the way, but this one you might not even notice. So there is still some plant diversity in the pond. There are large areas that don't have any plant growth at all, and most of those are either bare pond sediments or they're covered in some sort of algal mat, usually filamentous green algae, but again, as I said before, sometimes there are cyanobacteria mixed in too. And then we also did sample macroinvertebrates. Because macroinvertebrates have to live in these water bodies for a long period of time relative to a lot of other biology, so they're there for months to years even sometimes. They really reflect the long-term average of the water quality in a water body. If the water quality is not good enough to support them over a long period of time, or the salinity is too high, they're not going to be there. What we found, and we sampled in many different habitats, including emergent plant beds, submerged plant beds, and then sediments going from the western side of the pond to the eastern side of the pond, where you might expect more saltwater influence. We found freshwater species pretty much across the whole pond. And we found the highest diversity in the areas where plants were growing, but the highest abundance in the deep sediments. So there were fewer kinds of organisms in the deep sediments, but more of those organisms. So you might have thousands of organisms per square meter in the deep sediments, which means there's a lot of activity going on, but there's not a lot of different kinds of organisms. Whereas in the plant beds, the density was pretty low, but you might have had, 15, 20 different kinds. So that was kind of interesting to see. Primarily, the reason we were doing this was to see if the pond was characterized by tolerant or intolerant species, brackish indicator species. We didn't really see any brackish indicator species. We found almost entirely all tolerant species, which means they're used to having to deal with some pollutants. But they're there. There's something there. And then, of course, there's the Canada geese. We saw lots of resident waterfowl, and there were others, mute swan and mallards. But Canada goose was one of the ones that we noticed the most, often flocking in groups of more than 20 birds at a time. They are a potential source of bacteria and nutrients to the pond, and they kind of roam around and they turn grass into bacteria and nutrients that then get into the pond. Whether they go right in the pond or whether they're right next to it, it'll run off into it. They tend to seek open areas near the shoreline with abundant forage, so again, lawns are perfect. This one actually, here pictured, has a fence in front, but the geese were getting around the fence and able to get back there to graze. So one of the things we'll talk about later is if you want to have a fence, it's probably a good idea, but you got to make sure it actually keeps the geese out. Otherwise, they'll just hide back there and be safe and eat and poop on your lawn. Yes?
4-foot fence works pretty good. They don't fly over that often. The shorter the fence, they're coming over.
Right. And
Oops, sorry. Basically, the 4-foot fence does work. I put the 4-foot wire fence. And anything shorter than that, they fly right over all of the abutting yards. And then if the fence happens to fall down during a storm, they're in there, and they're in there for good. They won't leave. We got about a flock about 30 to 50 right now that are resident. So,
there is a certain time of the year where they are not able to fly because they're molting.
yeah.
And you may not be able to keep them out of your yard the whole year, but if you can keep them out at least that critical time, it may discourage them from hanging around and nesting in that area, which is kind of ultimately what you want to do. I don't think I've ever been to a pond where they're able to completely eradicate Canada geese just because there's always more that can come in, but just keeping them to a minimum is
Okay.
a reasonable goal, I think.
Yeah, they're heavy polluters.
Yes. All right, and now I'm transitioning it back to Keith, who's going to talk to you about modeling function of Bartlett Pond. And then I'll be back.
So the focus of my talk is really about phytoplankton and how they grow. And that is what this model was designed to do, is to model phytoplankton within lakes. Here is just a simple picture I put up of a phytoplankton bloom, pretty famous, Lake Erie, large phytoplankton blooms that occur there. And if you look at this, you might say, so why is there a bloom in the western part of Lake Erie and it's clear on the eastern part? There are clear reasons why blooms do occur in lakes, and we know that fairly well. For example, here we know that we have inflows from Toledo, Ohio, the Maumee River that basically drains all of northern Indiana. It's shallow, it's warm, and the phytoplankton get a chance to grow there when there are adequate nutrients. So there are some fundamental things that allow phytoplankton to grow. You need ample phosphorus, ample nitrogen, warm temperatures, so phytoplankton grow faster when there's warm temperatures. You need sunlight exposure, and you need time. So you put all these things together, and if you made them optimal, phytoplankton can basically double in a day. So they can have, if you have the perfect conditions, they'll double in a day. But fortunately for us, and so we know this fairly well, and how this is, we can define this. I've actually done experiments myself where I've taken lake water, spiked with phosphorus levels to see how they grew, and I had a nice curve of different concentrations of phytoplankton. Fortunately for us, most lakes don't have these perfect elements. They can't double in a day. If they doubled in a day, every lake would be completely green and we'd have phytoplankton blooms everywhere all the time. In the natural environment, we have variable conditions, right? And this is what kind of the focus of, a lot of the focus of the study was to define where the phosphorus is coming from and how much from each source. Where the nitrogen is coming from and how much from each source. So fortunately, we don't have perfect concentrations of phosphorus and nitrogen coming in all the time. This is a phytoplankton can double in a day. We have limited concentrations. They are high, like Matt pointed out, but still they're limited for the optimal conditions for a phytoplankton. So this is changing all the time during the year, and that's why we may have different concentrations of phytoplankton during the year and different growth rates. Another thing that might not be quite as obvious is time is really critical when this is all occurring. So if we have ample phosphorus and ample nitrogen and the lake is frozen, I don't really care how much phosphorus and nitrogen we have. The climate really has an effect on when they grow. And we have to have a condition where phosphorus and nitrogen are available when the phytoplankton can grow. So they have to have warm temperatures. They need to have sunlight, and this is fairly important. So midsummer, good sunlight, warm temperatures in midsummer, and time allowed to grow. This is something that I have discovered more and more for shallow lakes with large inflows, that this time element is really important. And this is what Matt described earlier, was the flushing rate of lakes. And it does matter for the lake, particularly last year when we had all these high flows coming in. So that time was much less than it would be if flows were much lower. So I'm going to get into all these pieces. And so if you, during my presentation, you'll see little clues about time and where and what in my presentation. Typically what you do, so modeling is really kind of this, when everybody talks about models, like what is a model? It's really just math trying to define how these different relationships occur, right? So you have a certain amount of nitrogen, and the phytoplankton can grow this fast. So it has an equation that defines those conditions. So when you do monitoring, you may look at the data, you may interpret it, and you kind of create some kind of understanding from that. But oftentimes, you don't know exactly what happened. You're just observing what is at that point. So modeling allows you to create a better understanding of what's going on, to connect the dots together, essentially, right? And so the secondary part of modeling is that once you've built your model, you can then do these scenarios, these what-if conditions, like what if I do this or that? How am I going to improve the lake? So that's what the purpose of modeling is, to get understanding of the lake. And then once you've built this model, you can then do simulations to figure out what can I do to improve it? And how much do I actually need to do to improve it? So for example, here's some monitoring data, right? So we have different concentrations. And you look at that and say, well, so it's phosphorus concentration in the lake, big deal. But if you just take one point here, right? There's so much going on to create that phosphorus concentration in your lake. There's all this stuff that occurred to create that particular concentration on that particular day. There's watershed inputs. Matt talked about the phosphorus and the sediment coring we did. So there's bottom sediments coming that could be contributing to phosphorus. There's groundwater. They did a very nice job of looking at groundwater. Oftentimes in studies like this, I don't get groundwater information like they got, and thank goodness they did. And then there are these internal processes like decaying phytoplankton and phytoplankton uptake. So basically this is the where, that determines what this is. And then there's kind of these internal processes that, although they don't seem as important, I wouldn't get everything right unless I had those internal processes kind of locking down the system. So you got to have all the pieces. You can't just leave one piece out. So you know how to know what's going on. So there it is. There's these different, I guess, inputs that create that phosphorus concentration. Behind those different inputs are all this other stuff. Your watershed and climate, so the watershed makeup, different climatic variability in the year. That's your watershed, dissolved oxygen, temperature, sediment, phosphorus, bottom sediments. All these things kind of go into these different pieces to define how the lake is working. So that was my role, is to take all the information in this computer model that I built to try to make sense of what's going on. So the question is, how do I know? So I can't put everything in the model. I have to pick and choose a little bit. But how do I know that my model's accurately representing what's going on in the lake? And so we do this thing called calibration, right? So these are the monitoring data. For example, this is total phytoplankton as chlorophyll A in the lake. And then this is the model. So it did a pretty darn good job of simulating what's going on in the lake during that year. And so if you can do this from the spring and the summer and the fall and get that right, you feel like, okay, so now I've locked down what's coming in the watershed and what's happening internally in the lake. So then I can have some confidence that I'm understanding what's causing these processes. So a big part of it is the water balance. There's not a lot to say here, but except we have a lot of inflows and outflows and fairly small groundwater inflows compared to the watershed size. It's still important. And then secondly, this thing flushes really fast. 3.2 days over the modeling period, right? That's pretty important, and I'll talk more about that later. And now I'm going to switch a little bit into some individual pieces that help us understand the lake. And one part was the water balance, and I pulled out from the water balance this groundwater piece. So ESS took some inflow data and outflow data, and my model took that data with evaporation estimates and precipitation and figured out how much groundwater was coming in all during the year. A couple points here is, here's groundwater coming in. It has this kind of, I don't know, what do you call it, upside down bowl shape, right? So you have groundwater coming in more in the spring and then less in the summer. It's more dry. More is probably going out than coming in, and then more is coming in. And then you may have these little spikes here. So this is my model simulated going on an hourly basis, and it actually matches pretty well what you measured in the field, which was nice to see. So we have a good feeling of what's going in. So the other part what's going on here is they took nitrogen and phosphorus measurements. So now we know what's going on in terms of groundwater inputs in the lake, around the lake, and also the nitrogen loads and the phosphorus loads that Matt was talking about previously. So one part, I'm not talking about all the aspects of the modeling that I did, but one important part is trying to figure out what is so-called controlling the growth of the lake, the limiting nutrient. And I want to make a point. One point I want to make is the phytoplankton aren't using either or, like they're not using nitrogen or phosphorus. They're always using both in that Redfield ratio that Matt talked about. They have to use both, right? So when they grow, they need both. But it's like trying to drive a car, with 3 wheels. It doesn't work. You have to have all 4 wheels. So if one's missing, it's not going anywhere. So if nitrogen is low, the phytoplankton are going to grow. If phosphorus is low, the phytoplankton grow. If they're growing, they're both using both. So they both have to be there. It's some situations one is limited or not. So in my model, I have a condition of a 1 and a 0. 1 is go, 0 is stop. So 1 means they have everything they need, they can double in a day. 0 means they have nothing that they need, they're not doing anything except dying off or not growing at all. So you can see that during the year this is changing, this limiting condition. So nitrogen and phosphorus doing about the same thing, and then in the year nitrogen is low and more limiting than phosphorus, and then later in the year they've been the approach. So you can see there's this variability going on, right? So that determines how fast they can grow. So one thing that was kind of interesting for me is now we have all this data in the model, and I'm simulating the phytoplankton growth, and I have so-called calibrated it, right? So that's my model data. That blue line tells me the concentration of chlorophyll A throughout the year. This is how it's growing, and then dying off, and then peak growth again. Oops, back. Peak growth again, and then it kind of dies off. Nothing really goes on past August and September. It kind of just stays low. This red line is what's coming from the nitrogen from the groundwater during that same period. And I think what we've noticed, I don't want to make too big of a deal, but what we've noticed is that when nitrogen is coming from the groundwater, the phytoplankton are doing pretty well. And then there's these periods where there's no nitrogen coming from the groundwater and they start to struggle and they stop growing, then nitrogen comes in. And it's not perfect correlation because sometimes phosphorus is limiting, sometimes nitrogen is, but oftentimes this nitrogen is determining the magnitude of these algal blooms, or algal growth, I should say. And then another point is, nitrogen is high in the fall, but it doesn't really matter because other conditions are limiting, right? So this is kind of what determined one piece of the puzzle of understanding what's going on in Bartlett Pond. Another thing that's quite interesting is this flushing concept. So this lake is flushing so much, it needs kind of a seed source of phytoplankton to be coming in to keep things growing, right? So these red dots are my estimated concentrations of phytoplankton coming into the pond, and this is my model, right? And so unless you have this seed source, the phytoplankton have a hard time getting going because they're flushing out so quickly. So if you have the seed source, they can grab onto this and start growing. And I've seen this phenomenon in several shallow lakes that I've actually modeled now. So the phytoplankton coming from the watershed are actually quite important. And it'd be really nice to be able to confirm this in 2020 to see how important that watershed seed source is, which would determine what kind of management actions you may want to take in the upstream watersheds. So I just want to talk about this flushing concept a little bit more, and then I'll leave it to rest. So the basic premise is that the phytoplankton need a chance to grow, right? So if they don't have that chance to grow, not much is going to go on in Bartlett's Pond. So high flows, the phytoplankton may have everything they need, but they're not going to grow fast enough to get going before they're flushed out. So this is like the basic equation of my model. It's really important. And it basically says how much phytoplankton growth you get in a day is depending upon your P limitation, your nitrogen limitation, temperature limitation, light limitation, which are zeros and ones multiplied together. For example, here are some 0, 1s that are multiplied together, and I get a 0.16, which is my overall limitation for phytoplankton growth per day. So what that means is it takes about 6.2 days, for example, in that one example, for the phytoplankton to grow, to double. Before they get to do that, they're already washed out of the pond in 3.2 days. So the climate in 2019 was really important in determining what happened to Bartlett's Pond. So I don't know exactly how it compares to past years in terms of the overall magnitude of phytoplankton in the lake, but it can have many effects in terms of the magnitude as well as the species and what's going on. So it's very important to recognize that climatic conditions can have a big impact about how we interpret what was going on in 2019. So that's a bit of understanding we got from the model. No, I lied. One more thing about the flushing. I apologize. So in my model, so I talked about previously, so once you build these models, you can do these what-if things. I did one kind of just out of my own curiosity and brought today. We didn't put it in the report, I don't think, but I just wanted to point this out. So here's 2019 flows. Here's my calibration. You know, the blue line is my model of phytoplankton concentrations measured as chlorophyll A, and the red are the actually monitored points. And then I reduced the flows by half just to see what happened with the model I built. And lo and behold, boom, the phytoplankton were growing about double what you got in other years. So your particular season or particular weather can have a big effect on how things are working. I should also point out that phytoplankton might be totally different in this kind of year. So I think Matt was, we had a discussion earlier about it could be, it's no longer the same kind of phytoplankton in a dry year. It may be cyanobacteria that are jumping in and need less nitrogen. So having comparative years of a wet year and a dry year really is a nice thing to have as possible to really understand what management actions you may want to take going forward. And just pointing out quickly, when I had the lower flows, you can see that the phosphorus concentrations in the lake were lower, the orthophosphorus, because the phytoplankton were pulling harder on the available phosphorus. Okay, I promise I'm done now. I'll let Matt take it home.
All right, so we're in the home stretch. I just want to make a few more comments before we move on to the presentation of the actual management plan. You know, what do we do about all this? So I know we've hit on it several times, but I just want to show you in more detail. 2019 was really an anomalous weather year. Looking down here at the bottom left, these are the antecedent conditions, so the 3 months of the end of 2018, October to December 2018. You can see Southeast Massachusetts was all in some shade of green, and that equates to 18 to 20 inches of rain just in those 3 months, or precipitation in those 3 months. So it was a wet period at the end of 2018. And then we started in on our study in 2019, and we had an even wetter period in 2019, at least for this part of the state, with really kind of extreme precipitation. So we're looking at 60 to 65 inches of rain over the last year, 2019. So it was a wet year. Flushing rate was very, very important to our study last year. If things were to dry out, it could change the outcome quite a bit. I think that point's been made very many times, but it doesn't hurt to make it one more time here. So let's just make sure we view the conclusions in the context of the actual weather conditions we had this year. It may not have been a typical year. We had almost optimal flushing of the pond with a pump that was essentially primed from 2018 before we even started in on the study. We also did something else as part of this study that I just want to touch on very briefly, where we actually looked at, what do we have in the watershed right now, and what would happen if we built out that watershed, so that all the available land, taking anything out that was already in conservation or was protected as a wetland or buffer, and just building out the rest of the watershed, what would that do to how much nutrient comes into the pond? So we know right now that Bartlett Pond, based on what we've sampled and what we have as data from the past, is a solidly eutrophic pond. So that means it's nutrient rich, and it has been for a long time, since the 70s. And it's been filling in, as we know too. What happens if the watershed is built out? So if you increase the developed area in the watershed, you go from about 47% developed among the parcels that are in the watershed to 69%. That means you have more stormwater and you have more septic loading of nutrients. At the end of the day, it increases your annual phosphorus load by about 250 kilograms a year. And just to put that in perspective, that's about a 30% increase over what you've got already. So that's you have a lot of phosphorus, that would be a lot more. Same thing with the nitrogen load. Now there's more nitrogen in the system. 2,000 kilograms per year would be about the increase. That's, again, more than a 30% increase in nitrogen. When you do that, basically you're taking Bartlett Pond from being a eutrophic pond, which is already very nutrient rich, and making it what's called hypereutrophic, borderline hypereutrophic. Hypereutrophic ponds really only end up not blooming with algae when the weather conditions are such or the flows are such that the algae gets completely flushed out. At that point, you're in really big trouble, because it means that you're likely to have more frequent and very persistent algae blooms. So that's a condition I think that, in this part of the world at least, we'd want to avoid, because it's one that brings a lot of potential risks with it in terms of algae blooms. And I've just put down here below some of the modeled scenarios. So right now we have a median chlorophyll A concentration of about 7 micrograms per liter, which is actually high, believe it or not. If you build out the watershed, you actually increase that substantially to 48 micrograms per liter. Same thing with the maximum chlorophyll A. This is your worst case scenario. Right now we're around 100 micrograms per liter of chlorophyll A. Build out, you up around 150. Puts you in solidly eutrophic to hypereutrophic conditions. So it's something we want to avoid. And if you don't do anything and the watershed continues to build out, that's where we're headed. All right, so with that in mind, what can we do? Now, we looked at a lot of options. I'm going to list them later on. And we kind of winnowed it down to the top few that we think are the most realistic at this point. These actions were selected to address the management goals for Bartlett Pond, and I'll just go over them real quickly. Improving the overall water quality, because we know water quality has been a concern at Bartlett Pond. Preventing or addressing harmful algal blooms. So we want to avoid them, but if we can't, how do we actually deal with them if they do occur? We want to avoid negative impacts to the recreational opportunities at Whitehorse Beach. And obviously it would be nice to have more recreational opportunities at Bartlett Pond too. And we want to maintain or improve the ecological value of the pond and prevent the establishment of new invasive species. So some of the management considerations we had to take into account. There's a lot of different challenges at this pond. It's not just one thing that we have to look at. We've got excessive algae, we've got high bacteria at times, we have lots and lots of nutrients, and we now have exotic species that are not in the pond yet, but are potentially coming in, and there could be others. So we think the management plan should include a comprehensive suite of suitable options needed to address these challenges. So you don't want to just get stuck doing one thing, because that probably won't address everything in every circumstance. We should have both short and long-term approaches, so things that we can do now, even before maybe we have all of the data in that we might want to collect in the system, and even before we're able to implement all the really long-term stuff that should be done in the watershed to manage these issues. We kind of need some quick fixes to help us bridge the gap. We also want to use both in-pond and watershed strategies. So we know we've got problems in and around the pond locally, as well as up in the watershed. So we kind of need to address it all to some degree. We want this to be designed to prevent future management issues, such as infestations of new aquatic invasive species. So we've got enough problems, we want to keep the new ones out. Provide a mechanism for monitoring of the system, so that the management approach can be optimized and updated and tweaked as needed. And then we've also got to consider the no action alternative. What happens if we just do nothing? There might be some benefits. There might not. There might be some consequences to that. But it helps put in perspective all the costs and risks that come with doing anything, because everything that you do has some potential drawback, and everything that you don't do also has a potential drawback. So we'll get into each of these in more detail, but I just wanted to give everybody an overview of the approaches that we selected and why. And as you look across this table, you'll see the issues addressed include algae, bacteria, nutrients, plants, and then other things. There's, sediments and other kinds of pollutants. So we want to make sure that the actions that we recommended address all of these things. And you can see we've got check marks in all the boxes going across. We actually end up selecting a number of potential options. So we've got these in-pond options, which include algicides, that deals directly with the algae, hand harvesting of plants, use of herbivores to control some plants, and then controlling resident waterfowl populations. So that addresses all the major management issues to some degree, just using in-pond or exactly, right next to the pond when it comes to the geese options. Then we have watershed options that we should look at. One of these is something that would need more careful study, but it's called nutrient inactivation, where you actually are able to inject a chemical to precipitate out potentially problematic pollutants, in this case phosphorus. Call that a dosing station. Septic system improvements in the watershed, and then stormwater controls, both for things that are already there as well as any new developments that might happen. And then there's other options that aren't really in-pond or watershed, but they're more generic things. And one of those is monitoring. It doesn't necessarily address the management issues directly, but it's necessary to know how you're doing and what's happening when you maybe change your management approach a little bit. And lastly, public education and outreach is something we always recommend, just because there's a component of this that requires people to be aware and engaged in the problems, so they understand what's going on and are aware of the issues. And it can address pretty much all the issues that are at Bartlett Pond, so to some degree. So let's take a closer look. Algicides, what are they? These are chemical formulations that actually kill algae. So they're not just pushing the algae out of the way or keeping them from growing. These are actually things that kill the algae. Most of them are copper-based formulations, such as copper sulfate or chelated copper formulations. But there's others too, including hydrogen peroxide formulations. They'll kill the algae quickly. It's guaranteed. Algicides will do the job. Relatively low cost per dose, and the permitting is usually pretty routine, so it's not too difficult to get a permit to do this. But they've got to be applied by a licensed applicator. They count as pesticides in the Commonwealth. Some of the pros, again, this is the fastest way to control algae, especially over large areas, and it's cost effective over the short term. Some of the things to think about when using algicides doesn't really address the root cause. So if you're killing the algae, as Keith said, they can come back in a pretty short amount of time if the conditions are right for them, if there's plenty of seed supply and they've got lots of light, heat, and nutrients. So it takes care of your short-term problem, but it doesn't really do much to address the long-term issues. There are possible water use restrictions with some of these. I'm not sure that's necessarily a big deal at Bartlett Pond. Most of them, they would just recommend not recreating in the pond during active treatment, just so that the applicators can actually get out there and do their jobs. And then I don't think this water is not being used for drinking, so that's not an issue, and it wouldn't be with a lot of these anyway. But there are some possible water use restrictions, so if there's a shallow well that you use for irrigation, you may need to be careful with that, something like that. All right, hand harvesting. Again, as I mentioned before, this is directly for managing plants. It's actually something that is very difficult to do on a large scale, but very easy to do on a small scale. So typically we recommend it as something to do as either preventative to keep new nuisance species from establishing in a water body. Once they're established, you can still do this, but the progress is going to be very slow, and it may not work, and people may give up after trying it a few times. So early on is the time to strike. Could be used to control both water hyacinth and water lettuce. You can pull them right out. They're not really attached to much. This would be preferred for most of our pioneer infestations of new species because it's minimally disruptive to everything else that's out there. It's easy to do. Most people can do it. There are professionals who do this, but for small infestations with the right organization, volunteers could also do it very easily. It does require dewatering and disposal, which is something that people don't always think about. So if you have larger infestations, you got to kind of plan ahead to make sure that that's going to happen in a way that makes sense. And again, the permitting is usually routine on this. One of the pros, it's selective. You can precisely control the species that you're looking for and not harm. There's not a lot of bycatch associated with hand harvesting. It's also simple, so it's intuitive. You know, like once you can recognize the plant and you learn the technique to pull it, you can do a pretty good job with it. So almost anybody can do it. Again, the bad things, or things to take into consideration, it's just cost effective for modestly sized beds. Once it gets too big, these beds get too big, hand harvesting really becomes pretty difficult to do effectively. And it's really insufficient for control of most established infestations because of this. You got to get them while they're early, while they're young, early on in the infestation. And then in some species, not so much with these that we're talking about so much, but you can potentially spread plant fragments and seeds. There are ways to mitigate this. There are fragment barriers that can be put up in case we were to get a species that was sensitive to this. But at this time, it's, you know, as long as we're harvesting at the right time of the year, shouldn't be a problem. Now, herbivores, this is something that we recommend specifically for purple loosestrife. There's lots of different kinds of herbivores that can be used for other kinds of plants, but you don't really have any of those at Bartlett Pond. So the only one that's really appropriate is purple loosestrife. This basically just involves introducing an organism that's going to eat the plant. In this case, the loosestrife beetle adults will eat the leaves, but it's really the larvae that bore into the stems and really weaken the plant. So you kind of need to establish a population of loosestrife beetles. This could be used potentially to control purple loosestrife at the pond. We have a pretty contiguous population from what we've seen. There's a lot of loosestrife in one area. That works really well for the beetles, so they don't have to fly all over the place to find another plant. They can effectively manage that compact infestation pretty well. Costs are typically really low. I mean, we're talking hundreds of dollars here to get 1,000 beetles. Permitting is routine. The nice thing about it is that the herbivores are a highly selective method, so they're species specific. That said, there are some rare species that Natural Heritage has concerns about with regards to purple loosestrife or loosestrife beetles. We're not aware of them being around, so it probably will not be a problem here. We're not in a priority habitat polygon with Natural Heritage at Bartlett Pond, so it's not going to be an issue. Some of the bad things, relatively few aquatic or emergent plant species are effectively controlled this way, so you don't have the same option for common reed, for example. And the predictability of the outcome is low. It's worked really well on some of the projects that we've seen in other places, like up in Westford, Massachusetts, and in upstate New York. But you don't really know until you actually release and monitor the beetles and the plants how well it will do here. Resident waterfowl control, so this is what we were talking about earlier. This has a really wide variety of control methods, everything from just running around and yelling at the geese, which works for a little while, but then they get used to you doing it and doesn't keep working, to just letting your grass grow a little longer. Fencing was mentioned earlier. Landscaping can be effective in certain cases. I'd say the most effective passive measures are fencing or vegetation. Keith actually made me aware today of a kind of an active method, which is a sprinkler that shoots the geese when it senses that they're there and shoots them with water to keep them from coming back. That's kind of cool. There's also deterrents that you can spread on lawns to keep geese from wanting to eat your grass, but then they might just go to your neighbors. So, there's a lot of different approaches. I think the point here is it probably takes a few different things to help reduce these resident waterfowl populations. One of the nice things is a lot of these actions don't even require a permit. They're just behavioral changes that we can make on our own. So another good thing, addresses a source of both excessive nutrients and bacteria. So I don't want to say you're killing two birds with one stone, but in some ways you kind of are. And the passive measures can provide secondary ecological, water quality, and aesthetic benefits. So if you choose to do plantings, you can have a nice garden that'll look nice to you and your neighbors, hopefully. May improve the water quality by the roots taking up nitrogen that's coming down off your property. There could be aesthetic or ecological benefits to that too, providing more habitat for upland species. Some of the limitations, fencing and revegetation really must form effective exclosures. So keeping the geese out to work if they're not high enough, or the lowest part of the fence is too high, they can just duck right under. If the plantings are not dense enough, they feel like they can see predators, so they don't get scared by them. You really got to design it the right way, and then if it doesn't work, be ready to modify it to help make it work. And it also takes a number of people doing it to really sort of keep the populations down at the pond as a whole and not just off of one particular property. All right, nutrient inactivation. This is one of the watershed controls that's sort of more involved. And again, if this is something that people were interested in moving forward with, it would really require a feasibility study first to make sure that this is the right option to go forward with, and that we actually have a location that would be feasible, and that the dosing would work. But in concept, it could work. So what it does, it targets phosphorus. A nice side benefit is if there's algae or other particulates in the water, like suspended sediments, it'll strip those right out of the water column too. So the water will look cleaner and you'll have less phosphorus in it. Involves addition of a flocculant, usually alum, aluminum sulfate. Polyaluminum chloride is also popular. There's others available too, including some that potentially have the ability to remove nitrogen, but that's not been really well demonstrated. These are generally chemicals that are used in drinking water treatment, so they have food grade chemicals available for this kind of work. Dosing station could potentially be used to remove phosphorus from the primary source, which in this case would be Beaver Dam Brook. I don't think there's really anywhere else that we would look at this point. We know that that's the primary source of phosphorus in the system. Finding the right location is the challenge, really, and figuring out how much of this material you would need to actually remove a sufficient enough amount of phosphorus from the system to make it worthwhile is the other question. The nice thing here is that the cost per unit of phosphorus removed is very low. So in terms of kilograms of phosphorus and the amount that's required to remove your first kilogram of phosphorus, typically with these dosing stations, it's under $100 a kilogram of phosphorus, which is very, very cost effective. Just to compare with some other methods, which we'll talk about later, septic systems and stormwater, those cost a lot more to remove phosphorus, or may not do a very good job of it at all. Stormwater could be several $100s to $1,000 a kilogram or more to remove a kilogram of phosphorus. As I mentioned, you need a feasibility study, and then if it is feasible and you decide to move forward with it, you really have to have careful design and siting to be able to permit this facility. It has been permitted elsewhere in Massachusetts. There's one in Wellesley that's operating and has been for over a decade. And there's another that we're actually working on in Worcester. So that one is currently in design stage. And it's been used in a lot of other parts of the country. It's been used for a long time down south, actually, where they have a lot more algae issues than we have traditionally. Again, the most cost-effective method of reducing the external nutrient loading, especially phosphorus, addresses the cause of excessive algal growth in the pond, so this will help reduce excessive algal growth, and it works quickly. When you put the phosphorus in, or put the alum in, it takes the phosphorus right out, and it really can't be used again for as long as, well, it really can't be used again for the foreseeable future. Ultimately, we're addressing the source, but we're really addressing the proximal cause. So there's still phosphorus coming in from the watershed. So this is maybe a step better than the algicides, where you're just killing the algae because you're actually dealing with one of the causes, but you're not dealing with where the phosphorus is coming from in the watershed. So that's one drawback to this method. That said, it could be a very effective bridge method, or a way to get phosphorus reductions where you can't realistically get them in another way. Now we want to talk about septic system improvements, which includes repairs, upgrades, and more frequent maintenance of on-site wastewater systems. Now, there's a lot of different kinds of systems out there, and I won't go into detail about all the different kinds and their advantages and disadvantages, but there's lots of ways to do this. And so I think the take-home message here is, if there's a system in place which allows for improvement of these systems over time, so that you're reducing the loads into the pond, you'll see improvements. And that's really what we kind of want to get at, but it might take a while. It may also include regulatory changes, so not just the actual installation of these systems, but maybe changes to the regulations. And what we are targeting here is excessive nutrients and bacteria, so that's good. Again, we're killing two birds with one stone. Some of the drawbacks, improved systems may reduce septic loading, but you're not going to eliminate it. So if you have septic systems, maybe short of a tight tank, eventually something's going to get into the groundwater and eventually into Bartlett Pond. So maybe you're reducing how fast it gets there or how much gets there, but there will still always be something. And it really requires large-scale adoption to have a measurable impact on in-pond water quality. Unless somebody has a failing system that's just emptying right into the pond, all of these are going to be incremental improvements. So it takes persistence over time. And then again, there's the cost. The cost could be very high, especially for individuals that have to either improve or upgrade the system to actually get these improvements in water quality in the pond. But these are going to vary a lot by residents, so it won't be the same for everybody. Now on to stormwater improvements. So this addresses more, if septic addresses the groundwater loading issues, this addresses the surface water loading issues through stormwater improvements. We often refer to these as best management practices, or BMPs. Green infrastructure can be incorporated into stormwater designs. You can have porous pavers, as seen here, and bioretention, which involves the use of plants. There's lots of different approaches to stormwater improvements. Again, these can also include regulatory changes to either require or encourage developers to incorporate these into their designs, both during development or redevelopment projects. And the targets of each stormwater improvement type actually differ quite a bit. Some features are very good at removing bacteria or sediment, whereas others may be really good at removing nitrogen or phosphorus. So there's like kind of a different flavor for everybody. And what determines what you put in, there's a lot of things. It's what's coming from the source, as well as what's actually feasible to go into that location. The good thing here is we're addressing watershed sources of a really wide variety of pollutants. If we put in stormwater improvements in a lot of areas of the watershed, these can be designed to reduce or attenuate stormwater discharge volumes, which also reduces flooding, which is a good thing, and can be used to reduce the impact of new development. So that build-out scenario that we saw might not be so bad if everybody had really high-quality stormwater designs going in. That's usually not, it doesn't end up being the case with all development projects, and so you don't always get, the best-case scenario, especially over time. That's one of the drawbacks too. The maintenance costs on these are high. So you put them in, they might work well for a little while. Some kinds need to be maintained very frequently, quarterly, monthly. Some you can go a year, but they all require inspections and maintenance. And retrofits especially, where you already have stormwater infrastructure and you're trying to fix a problem that's already there. Because there's infrastructure there, those can be very costly and may have low cost effectiveness. You may not be able to get a lot of bang for your buck. Doesn't mean that you shouldn't do them. These are just things to think about. And finally, these generally require large-scale implementation and time to have measurable impact on water quality. So you can make improvements in the watershed that you may not see for a few years. We talked previously about public education and outreach. One of the nice things is this can be almost anything. It could be informational kiosks, could be social media postings, could be a link on the town's website. It could be all different kinds of things, workshops. But really focuses on raising awareness of issues and benefits of behavioral changes in the population here. Can also include public participation too, and that's really actually recommended to get people really interested and involved in making a difference in what you actually see in terms of water quality. Tends to be very cost effective. Some public education programs don't cost anything. Allows the community to stay informed and may lead to some improvements in water quality or biological condition of the pond. Unfortunately, some of the improvements that you gain are usually likely to be very marginal, and they take time to be realized. So you might fix 5 to 10% of your problem with public education and outreach, but you're not going to get all the way there. So you need to combine it with other things to really be effective. And then our monitoring program, again, I mentioned that this is something that's really not a management action, but it's required in order to, first of all, be able to develop the appropriate management actions, and secondly, to be able to make sure that what you are implementing is having the desired effect, and whether you need to change anything in your management program. And then finally, looking at the no action alternative, which is not recommended here, just FYI. This would include avoidance of all the management actions that we just discussed at Bartlett Pond, and would likely result in the following: unchecked algae blooms, establishment of aquatic invasive species, further degradation of water quality, reduction in aquatic habitat volume, decreased recreational opportunities, decline in aesthetic value, and conversion of land underwater to other wetland types as the pond continues to fill in. I guess the only thing it has going for it really is there's no immediate monetary costs, but you're kind of just kicking the can down the road. Eventually these things will pop up and become bigger issues. Doesn't really address any of the current or foreseeable future management challenges at Bartlett Pond, so you're really not gaining any traction with those. I won't go through all these, but here's just a list of some of the other things we considered, but we have not currently recommended. It's a long list, and this isn't everything that's available. These are just the things that we thought were even marginally applicable to this pond. I think we're through. So now it's open to questions. And I'm sure any of us would be happy to answer your questions.
What is sonication? Sonification?
Sonication?
On that last,
Yeah, sonication is the use of ultrasound to disrupt structures within algae cells that causes them to not necessarily always die right away, but sink, and then eventually either senesce or at least not be reproducing as quickly. So it sets the algae back.
as far as cost goes, what's that to dredging?
What's that compared to dredging? Well, it really depends on how big the dredging project is.
Okay.
But, you know, with almost any dredging project, you're talking several $100,000 at a minimum. Sonication, probably going to need some studies to figure out what exactly kind of unit you would need. And the units are probably going to run in the tens of thousands, maybe, thousands to tens
So
of thousands.
sonication, is this something that's continuously done?
You mean it's out there operating all the time?
Yeah.
Yeah, well, it would be operating when you need it, because it does use power.
Yeah.
So that's one of the drawbacks of sonication. The other thing is it needs a clear line of sight. So if you have a point that comes out, that you can't sonicate beyond that. Your process only shoots in that direction, and if there's something in the way, it won't get past that.
So my question is, if you do dredge it, right, and you increase the volume, right, and you take the nutrients out that are harmful or whatever, would that be advantageous to the whole environment?
Well, I guess the issue with dredging is you might take the nutrients out that are in the sediments right now, but because we have so much coming in from the watershed and a little bit coming from the sediments, but not that much, you don't get a lot of nutrient benefit from dredging in this particular situation. You would get deeper water,
Yeah,
at least for a time,
till it fills in again.
until it fills in again. Yeah,
Okay.
exactly.
Thank you.
Are these typical results of what you see in other places that you research? Is it better? Is it worse?
That's a good question. I'd have to say, in terms of the phosphorus levels in particular, these are some of the highest I've seen outside of a very urbanized system. And, you know, this is somewhat urbanized, but not, it's not like a concrete jungle. That said, I think it's unusual in that we have such high levels of nutrients and we didn't see bigger problems this year. But I think we have an idea as to why that might be, and I'm a little concerned that it might not be that way every year. But we don't really know because we haven't studied the system enough. We've only seen it under these conditions, so we don't really know what caused the bloom in 2018 or what might trigger that again in the future. It could be something different.
Is your study over, or how long do you continue?
Well, this is the final project report. But
Thank you for that presentation. It was great. Yeah, I have a couple of things. Going through this process with problem, I should say, this problem with Bartlett Pond. It's been going on for years. So am I correct to assume that we really should be directing our questions to the town? Because that's where we need help to get some of the things done to eliminate some of the problems that we have with Bartlett Pond. Like, the dredging is an important thing, and I'm just wondering, is it possible for the town to commit themselves to dredge it twice a year? Is that something that can be done? I don't know if Karen or Dave can answer that. How would that work? Is that?
So without thorough permitting, you could not commit to dredging. Dredging would typically happen after a coastal storm event, which would prevent outflow of the pond and potentially increase the surface water of Bartlett Pond, flooding adjacent properties. But just to dredge a pond, for dredging the pond's sake, would have to go through extensive permitting.
Okay.
You'd also have to, in addition to the sampling that's been done, you'd also have to do a thorough sediment sampling for chemical analysis to make sure that wherever you were disposing of that was done properly. And depending upon what you find in the chemical analysis will dictate the disposal costs, so that could significantly increase the cost of a dredging project.
Is that something that we can, look into or work on in case we need to have that done, maybe once or twice every year? Or do we wait till we have a backup that is necessary? What's the
Dredging
best?
typically doesn't happen once or twice a year.
Okay.
Dredging is something that, when it's done, is typically something that's done once
Okay.
in a great while, merely because of the capital investment that occurs. Now, certainly the harbor's not the best example because it's a different environment, and you certainly wouldn't want to go 50 years without dredging, but typically that's somewhere in the more of the, 10 to 20 years it gets done, not twice a year. I think a cost to dredge a pond without knowing any of the sediment chemical analysis could be pretty steep in price.
Thank you, Dave. My other question would be, I'm sorry, I have a couple of them.
Sorry.
It's probably going to go to the Board of Health. I'm not sure. But up in Bartlett Pond, well, of course, a lot of these homes were built before, they really shouldn't have been because of the wetlands, but it was done before the Wetland Act and whatever. And talking about septic, okay, and there's a lot of people that are still, as of today, still have cesspools, which is still considered an illegal septic system. How can we reach out or do something to those who live in that area to get them up to be updated on their septics, whether they should be cleaning out every year or every other year the most, and see if they're in good working order or whatever, I mean, is there something that we can do to, address the Title V to these residents who live in that area? I'm not saying that that's the whole problem which
Right.
causes this, but, a little bit of this and a little bit of that goes on up there is what contributes to this problem. Because we know that the pond is not owned by the town. It's not. But when we have these backups and it goes out and comes down the brook, okay, now it goes out to White Horse Beach, which then the town has jurisdiction over that. And then we're hit with the brook problem with the summertime, with the children and whatnot. So I'm not saying that the septic system is the 100% cause of this, but is there something that we can put into plan to maybe try to reach out to address that issue?
Yeah, absolutely. We can certainly put together by street and then do research as to what properties there don't have would be considered a Title V compliance system. Then notify those homeowners that they would have 2 years to bring their systems into compliance.
Okay, and my final question would be the building. I know we've been doing a lot of building in Plymouth lately, and there is a lot of building going on up in that area. That, after you see this presentation, how you see it's like a dominoes effect, the water, the flow, the this and that. I think the town needs to be careful now on where they're building these homes, especially 30, 40 units and so on and so forth. So I'm just saying, maybe, the town should be a little bit more considerate as far as where they're allowing these permits to build these homes. Okay, thank you so much. I appreciate it.
You're welcome.
Can I make a comment
Sure.
on Alice?
Absolutely.
Alice, if they do Bartlett Pond, picking out just the people that live there for their septics, you would have to do that basically for the entirety of everybody that lives on the pond, lake, or stream. And not that I disagree, it's just that it sounded like you singled out the people on Bartlett Pond.
No, I wasn't singling it out, but it's still a situation where there are people that live around that pond that contribute to that. All I'm saying is that if there's a lot of people there that are not doing their job and taking care of their septic systems and not having them pumped or whatever, that's still a contribution to the problems that we're having. All I'm saying is that they still should be notified. You may be great, but your next door neighbor may not be. We still have those problems. If we all try to buckle down on, certain things, it eliminates some of the problems that we're having and what we're complaining about. So it's everybody's problem. It's just not one issue. That's all I'm asking. Thank you.
Just make sure you press the green button.
It's the green button's on. Cheryl Kingfisher, I live down in Manamet,
And first of all, thank you to ESS, and thank you to the town for funding this particular assessment. It is very comprehensive, and there's a lot to take in this evening. So I know that we're going to have to study it some more. I have a couple of basic questions, and I guess the first is I did not see, and perhaps I missed it, some breakout of an estimate of the different amounts or the different sources of the phosphorus and the nitrogen. In other studies like this, I have seen a circle graph that says we estimate that X comes from the stormwater and Y comes from other sources of the phosphorus that's being released in the pond itself, and Z comes from septic systems. And so did you do that, or will your modeling give us that kind of a sense of where the bigger of these big problems are and the smaller of these big problems are?
Yes, so I actually have the numbers here. So 91% of the phosphorus load comes from surface water, which is Bartlett, or Beaver Dam Brook.
Okay.
And 8% is internal loading from the sediments.
Mm-hmm.
And then 1% of the phosphorus is coming from groundwater, which
Okay,
includes septic or any other sort of sources in the groundwater.
Okay.
So that's for phosphorus. For nitrogen, it's more like 80% surface water, so that's the brook coming in, and then 20% groundwater. And I think in Keith's model, you can kind of see that when you get those slugs of nitrogen coming in through groundwater, that's when we tend to see more phytoplankton growth.
Okay, so my second question is, how can the residents and how can the town begin to come up with some sense of priority in choosing the solutions to tackle first and those to tackle second? Where do we get the help with that? Where do we find, how do we do that? I'm getting to that part.
Yes, and
In what form? Is this something that the health department should take on, as its next project? Or how can we take the great information that you've given us here, take it to the next level of analysis and begin to select or come up with a list of priorities so that we can then begin to cost them out? We don't need an answer tonight.
Well, I mean, there wouldn't be one.
Huh?
There wouldn't be an answer tonight,
No,
because
I know.
what it really does come down to is getting us, different departments getting together, working together, reaching out again to the residents, the working groups, and putting together those priorities, and then figuring out, I mean, there might be some quick hits, maybe the fencing for the geese, might be a quick hit. Interesting fact, each goose is responsible for 20 pounds to 30 pounds of waste a day.
Right. Right.
So,
And, and volunteers could do some weed pulling. That's been very effective in a number of other places, so that's an immediate thing that can be done. I guess my third question, and then I'll go sit down, is that I'm looking at the nitrogen and phosphorus that ends up in the groundwater surfacing into the surface water, thus coming down the brook. And we know that, a lot of it, as Alice has just said, or some portion of it, is coming from the on-site septic systems. And the town, in its 1982-83 study that got this particular round of inquiry moving forward, went through the conversation that the community actually thought about sewering the whole area out there. And so might it be worth taking a look over the next, X number of months or whatever, and doing an economic evaluation, pros and cons, of putting in some kind of community septic there. We have a community septic out in Pine Hills. We have other large developments that are doing their own package plants. Maybe the time has come for that whole neighborhood to think about some kind of community system they're going to tie into. Because if some number of the homeowners are going to be forced to upgrade their systems and spend $30,000, $40,000, $50,000 to do that, it might well be cheaper in the long run for them to tie into a sewer system that, you know, may or may not make it over Pine Hills into the town's sewer system, and I don't know how much capacity we have there. I haven't checked that out, but I throw that out to the community, and you know, as a town meeting member who represents Precinct 6 and votes on budgets, and as someone who lives down there, I am more than interested in helping the residents have a conversation about that possibility. That's it for me. Thanks.
I just have a quick question about the 90%. Are you saying that comes from before the pond? So
Correct, yeah. There's
the problem is
90% of the load is coming from the brook itself into the pond.
so we need to look at septic systems, not even just the pond, way before the pond then.
They're probably a component of it. How much, we didn't really, that's sort of beyond the scope of the study that we did. But there are other sources too, in addition to septic systems, so I don't want to make it sound like that's the only source or even the primary source at this point. It is a source.
All right, thank you.
Just for clarifications, so that everybody understands, I was not trying to just say that it's just those who live up at the pond, that was where all the problems are with the septic. It is all over. All I was trying to say was that it would help if these people were notified, because I know where I live down on Taylor Ave, down on the beach side, I know people that have been there 30 years that should have got a septic system 28 years ago, 2 years after they paid cash for it, because when you buy something for cash and it's on a cesspool, you have 2 years to get a septic system. And I can tell you right off, they don't get them. They don't get them, and the state does not have the time, and they don't have the effort to go after everybody in the state of Massachusetts to update their cesspool to a septic system. So just for clarification, I'm not saying this is strictly, you know, a Bartlett Pond resident. I'm just saying if they could reach out to try to eliminate some of it. Absolutely, it goes everywhere. Thank you.
Hi, I'm Barry Potvin, the Vice Chair of the Board of Health. Just a few comments and suggestions. One is, this is a much broader problem than just Bartlett Pond, because there have been cyanobacteria blooms, both seen and probably unseen in other bodies of water around Plymouth. I know one is Billington Sea, that's had a major problem with this same sort of thing. Also, general comment, as everybody knows, this whole study was initiated, and your report was incredibly detailed and thorough, by the way, so thank you for that. But it was all initiated because of the 2018 very troubling cyanobacteria bloom, which everyone felt was an emergency. So given that that seems to be caused, at least in part, by the high phosphorus, high nitrogen levels, apparently Bartlett Pond's water level has gone down precipitously in a fairly short period of time. Most likely the water temperature in Bartlett Pond has also increased as the water level goes down. And probably also the oxygen levels aren't very good there as well. Seems to me from your descriptions of the various options that one of the most effective ways to pursue this, which might be most cost effective, would be to look into those dosing stations for nutrient inactivation. I don't know how many of those dosing stations would be needed. I don't know the costs that would be entailed. I know there would have to be an initial study to make sure it was feasible. But you mentioned that it had already been done in Wellesley and Worcester, or at least you're in the process of designing one for Worcester.
Right.
Do you have any other information about how big a problem they had, how effective this was, what the total cost might have been, how long it would take to put something like that together. Obviously, this is an ongoing problem. As you mentioned, this was an unusual year, and there was a lot of flushing in Bartlett Pond. That's not going to happen every year. It's obvious it probably didn't happen in 2018, and look what happened. This is not something you can kick the can down the road for. It's going to keep happening unless we do something about this, and it needs to be effective in both the short term and the long term. So for the short term, could you give us more information about the dosing stations?
Sure, yeah. So typically, in a case like this where you have one primary tributary, because you asked a question about how many dosing stations would be needed, you probably just need one location. And in terms of costs, there's design that needs to go into it, as well as the construction costs after you've determined it to be feasible. I mean, all in, it's going to be probably a few $100,000s to do the feasibility study, design, permitting, and construction. And then the operating costs sort of depend on commodity prices, because what you're buying actually is, it's aluminum, essentially. So that can vary, how much you add depends really on how much phosphorus you need to remove and what time of year you're going to do it, and how long you're going to do it. So there's a lot of variables that go into that, and that's sort of some of what would be figured out by a feasibility study. You get some of those numbers a little bit more concrete.
Okay. Was the system that was installed in Wellesley effective?
It's been very effective. So they used to have to close the beach. This is at Morse's Pond in Wellesley. They used to have to close the beach very frequently because they had algae blooms that actually limited visibility in the pond to almost nothing. And they've been dosing it, again, over 10 years. I don't remember exactly how long. They've switched around a little bit. They started as sort of an experimental plant that used alum and sodium aluminate, and that was kind of messy, and they found that aluminum chloride was a better choice, so they switched to that in the last few years. But it's been very effective at maintaining the higher transparencies and reducing the likelihood of algae blooms in that pond.
Do you know of any grants that would support this kind of effort?
Grants that would support this specific kind of effort? The 319 program is designed to remove phosphorus or address phosphorus and other non-point sources. I don't know if a dosing station would qualify. I know they have funded in-pond nutrient inactivation projects before, where you actually take a boat out and dose the pond. At Bartlett Pond, what you would get from that is sort of uncertain, just because, again, there's such a high flushing rate, and we found that there was some phosphorus loading from the sediments, but it wasn't the majority of the load, so it seems like a better place to focus, if feasible, would be the tributary to the pond first. But yeah, grant funding might be hard to come by for that sort of thing.
Okay, thank you.
Yep.
Are there any other questions from the audience? Members of the working group? Okay. All right, well, that concludes our presentation tonight. I want to thank the group from ESS for coming out and sharing this information with us. To let everyone know, a copy of the presentation is on the website. You can access it through the town's website, which is plymouth-ma.gov. Go to departments, find public health, and click on public health, and you'll see you can link right onto the presentation for those at home that might want to take a look at it, or those in the audience who do not have a copy tonight. Thank you very much.